So I would be remiss if I didn't mention a few reactions before proceeding on to the next module. The first thing I want to talk about is a usefulness for halohydrin products. And sometimes, I'm sorry if I pronounce it halohydrin and that bothers you. Many people call them halohydrins and whatever. Anyway, so halohydrin products are, again, when we've got an OH next door to some sort of X, where X is Br, Cl, I, that sort of thing. What we can do with these is we can actually just treat them with base to form an epoxide. Kind of nice. So epoxides, full circle, right? Well, I guess we started with ethers, but you get it. So this chemistry is actually very similar to the Williamson ether synthesis. This is just an intramolecular, or within the molecule, Williamson ether synthesis. Namely, if we look at the mechanism for this, what we're doing here is we're treating this with some sort of, I better be careful, some sort of base minus. I'm just going to redraw this down here. Let's just do that. Okay. Because I want to stretch out the oxygen-hydrogen bond. And now if we consider base minus, what it's doing is it's going to deprotonate the oxygen, if we choose a good base, to give us an alkoxide, which is then going to add intramolecularly to the carbon bearing a delta positive, pretty good electron accepting sigma bond, to push the electrons over to the halogen, which serves as a leaving group, to give rise to our product. Now, how would you actually do this? Well, you'd probably use sodium hydride. It's really an ideal base for this reaction. And if we look at a specific example, what we could do is, let's first of all take cyclohexene, react it with Br2 plus H2O. That would convert the alkene into a halohydrin using the reaction we looked at last time. So there's our halohydrin reaction. We also form the enantiomer. You can just draw one and go forward with one. And again, we can have the Br and the OH on opposite sides in this case, because I don't have the methyl group, to make one side more substituted and less substituted, as I showed in the previous lecture. Okay, so what we could do going forward with one of these is we could add sodium hydride. And if we add sodium hydride, we think about that as being like sodium bonded to hydrogen through an ionic bond. If they dissociate, the hydride can deprotonate the acidic hydrogen from the alkoxide. That's going from the alcohol, excuse me, to give an alkoxide. And these two are actually perfectly positioned to do the intramolecular reaction to give rise to the three-membered ring, where in this case we have both dashes, but if we went forward with the opposite enantiomer, we'd have both wedges. So you could just draw either both wedges, both dashes, or just straight lines if you want to ignore stereochemistry of this reaction, because that just implies to me that you know you form a racemic mixture. So both enantiomers would be formed. So what I've done here is I've done two steps to convert the alkene into an epoxide. There's actually a more straightforward way to do this. You can actually go to an epoxide directly from an alkene using a reagent called MCPBA, a specialized reagent. Known as MCPBA. Will convert alkenes directly to epoxides. So MCPBA is a reagent I want us to know for the next module, but I want us to know what it does now. So if you see MCPBA or this structure, I want you to know what this molecule does. But we'll worry about the actual, like, what MCPBA stands for when we talk about benzene rings, which I believe is the next module. I should check into that. Okay. Now, the important feature of this molecule is the peroxide. This peroxide is what facilitates formation of the epoxide. So the peroxide does the work. The chlorine, the carbonyl, and the benzene ring just make it an easier to handle peroxide than hydrogen peroxide, which just kind of goes bad over time. So what we can do with this is we can actually take our alkene plus MCPBA to make, and we could draw this if we want. I know you want to. Our epoxide, which could be shown as either enantiomer or just the straight lines to imply to me that we have a racemic mixture. Okay. Now, the mechanism is actually one of these where it's highly complicated, but restricted to mostly a single step. So I'm not too worried about pushing the arrows. But if we wanted to, and I know we want to, we could consider the curly arrows just for the sake of discussion. Let's go ahead and put a minus and a plus on either side of what was the carbon-carbon double bond, just to redepict this molecule as a resonance structure. Then what I'm going to do is I'm going to have an oxygen get close. Now this is the outside oxygen of MCPBA. MCPBA forms an intramolecular, or within the molecule, hydrogen bond between its carbonyl and its peroxide hydrogen. This hydrogen bond exposes the exterior oxygen to promote the transformation that you're about to see. One way to think about this is the negative charge adds to the oxygen. Why would it do that? Well, that oxygen is not stable. It has next to it actually a fairly good leaving group, which is an oxygen part of a carbonyl, as part of a carbonyl. So we can push the electrons from the oxygen-oxygen bond to make a carbon-oxygen double bond. To avoid breaking the octet at the dotted carbon, we're going to push the electron density up to the H bond to actually make a bond with that hydrogen. And then the hydrogen-oxygen electrons are going to come down and add to the positive charge. So cumbersome set of arrows, complicated set of arrows, but within a single step, we form a carboxylic acid, MCBA, as opposed to, we no longer have the P, peroxy, in the MCPBA. So we have MCBA and an epoxide. So one step, a lot of arrows, one step. It's dictated by the orientation of the hydrogen, that the hydrogen bond kind of exposes that peroxide oxygen. This is possible with other reagents. I really like MCPBA. In a normal semester, we try an MCPBA lab. Okay, so just some cleanup with this reaction is we do need to pay attention to the stereochemistry of the starting alkene, because that will determine the stereochemistry of the epoxide product. Now, both enantiomers are formed, but how do you know which diastereomer, which combination of wedges and dashes you'll form? Well, it's actually pretty straightforward. What we have is, if we start with a E/trans alkene, and we react this with MCPBA, we will form an epoxide where the methyl groups are trans to each other. And similarly, if we started with cis, we would get cis. And the reason why this works this way is because our epoxide in a three-membered ring, the bonds to the epoxide must both be the same, both be wedges, both be dashes, or if we orient them as straight lines, it allows us to see the wedges and dashes of the things attached to the epoxide, and those will remain consistent from the starting material. So if we add MCPBA to this, we would get here and here, plus, and due to symmetry, these are the same. And so we get both combinations of trans or both combinations of cis if we start with something that is known to be only cis or only trans. Now, if we had multiple groups, we should kind of be aware of the relative relationship of the two. That is, I would call this an E alkene because we have 1, 2, if we cut this in half, and then 1 compared to hydrogen, which is 2. If we react this with MCPBA, what we see is that the ethyl group and the methyl group must remain on opposite sides of our epoxide. That is, if I have my epoxide with an ethyl group out, the methyl group on the same carbon must also be out, but the hydrogen must be on the same side of that ethyl group, which is opposite of the methyl group. And we could get either enantiomer of that, so we could flip everything. Okay, so either enantiomer is formed, but not the diastereomers, not where we mix and match, where we've got the ethyl group on the same side of the methyl group on the opposite carbon, and then the hydrogen on the opposite side. So not this. Plus one where we flip all the wedges and dashes of that knot structure. Okay, very last reaction of the module is one of my favorite reactions. It's a great one to end on. It's a fun puzzle. It's the ozonolysis. Oops, sorry. It's the ozonolysis of alkenes. So ozonolysis means ozone to break alkenes. And what we're going to do is we're going to convert the alkenes to 2 times a carbonyl. Gosh, this is such a cool transformation because it's a transformation that uses a readily available gas and does a dramatic transformation. Okay, so no detailed mechanism is required for this. Instead, what I want you to do is be able to solve the puzzle, predict the products. If we've got our alkene and we add it to O3, O3 is ozone, we're going to crack the alkene in half. And if I've got square carbon and starred carbon, we're going to have, which are alkene carbons, we're going to have a carbonyl derived from the square carbon plus a carbonyl derived from the starred carbon. If you notice, I could have drawn those carbonyls like this, but I actually prefer to have them slanted at the same angle parallel to the carbon-carbon bond from which they were derived so I could see how the product formed. Okay, now for this reaction to work, we critically have to add a molecule of dimethyl sulfide. Dimethyl sulfide, this reduces the intermediate and makes DMSO, dimethyl sulfoxide. It's kind of a weird sulfur structure. So you use O3 and dimethyl sulfide and you can do this transformation, and gosh, it is cool because ozone, you can just blast the system full of ozone. Okay, so Where does ozone come from? Everybody knows the smell of ozone, I bet. Ozone happens when you take O2, well, let's do some stoichiometry. Two O2s, three O2s, there we go, plus lightning bolt. That's terrible, sorry. Plus electricity gives two O3s. So if we take electricity and static discharge and apply it to a system that has some oxygen, we will form O3 at this stoichiometric ratio. So when have we ever done the experiment where we've applied electricity to oxygen? After a thunderstorm. You know that kind of fresh smell after a lightning storm when you go outside? That's the smell of residual ozone in the air. Now, ozone's super cool. It's super bad for us in concentrations. So a lot of times when they show the air quality report on your phone, that is the ozone content amongst other things. But I mean, we've evolved to kind of be good at dealing with it as long as you're not in the lab doing an ozonolysis reaction without ventilation. Okay, so what happens? The other thing that's cool about ozone is it's blue. Okay, hello atmosphere. Okay, so ozone is blue. So what do? So when I set up an ozonolysis experiment, I've done a lot of these, and they're super fun. You take your alkene, you put it into a flask, and you blast oxygen through an ozonizer and into your reaction tube. Now what happens is after you're all set up and you can see the oxygen is efficiently bubbling through your reaction with your solvent, you turn on the electronic discharge, the static discharge in your ozonizer to convert those oxygen atoms into some concentration of ozone. The ozone comes in, it rapidly is consumed by the alkene, and it just keeps reacting. So you're sitting there watching, and it just looks like nothing's happened. You have good ventilation, so you can't smell the ozone. That's bad because the ozone would displace the oxygen, you'd die. Okay, good ventilation, you can't smell anything, you can't see anything. After all of your alkene has reacted and the ozone has nothing else to do but saturate your reaction mixture, the reaction mixture is going to turn a very cool, vibrant blue. That is the indicator that your ozonolysis reaction is complete. You turn off the static discharge and let the oxygen continue to bubble through until the color has dissipated, indicating you have safe levels of ozone in your reaction. You can then remove your oxygen input to just have a stirring reaction mixture that's now clear and loaded with a ton of super scary peroxides. You add in your dimethyl sulfide as a super stinky reagent to kill the peroxides, making it safe to handle later on. You'll get some residual smell because you always add a little too much of the stinky dimethyl sulfide. But once it's oxidized, it doesn't smell anymore. Super cool stuff. And then you've got your dramatic transformation. How dramatic? It works on any alkene that's not a benzene, not an aromatic system. And in fact, we could have things with multiple carbon-carbon double bonds or things that are inside rings. So if I had this molecule, cyclohexene, I would get the 1, 2, 3, 4, 5, 6. I would get this structure. This is hard to see. So instead, what I want to do is I'm going to draw the original ring, but have like a little break and then put two oxygens where the carbonyls are. Both of the alkene carbons get to be an oxygen. That allows us to better visualize the product. That's formed. So this over here is easier to see. Another way of thinking about it that I was taught is I'm going to draw two little oxygens inside the carbon double bond and then just yank those apart to form the final product. Two carbonyls in place of the carbon atoms that were bonded by an alkene. And we can apply this strategy to something a bit more complicated. What if we have a benzene that's attached to a cyclohexene that has two double bonds now? The benzene is not ozonized, but the other two alkenes are. So what I'm going to do is I'm going to really get in there. I'm going to draw my two small oxygens. Then I'm going to redraw the structure, maybe a hair bigger, Okay, the benzene ring I don't worry about. We're not going to break aromaticity. But now I'm going to draw this bond as 2 carbonyls. So I really stretch this out. Then a carbonyl here, plus a carbonyl here. So we form formaldehyde as a byproduct, but these are now the 2 products. So by doing one transformation, we convert 2 alkenes into 4 carbonyls, and carbonyls make up the majority of the chemistry that we talk about in this class. And so to say that we make a powerful functional group is a vast understatement. All right, there it is for module 2. A great one to finish up on. Look at some practice problems that you can kind of see. I really like the 2 circles inside the alkenes. If you have trouble with this, let me know. I love talking about helping solve problems related to ozonolysis.